Okay, right. How's it, boys and girls? John Mundelbauer, owner of Bauer Research here, and I'm going to do hopefully a better presentation of this conservation of angular momentum fallacy. Basically, all the maths is on the board and it's nice and big, so hopefully we can see it better. And I'm just going to go through what is a classic demonstration used in many physics classes, supposedly to demonstrate conservation of angular momentum. So it's an object on a string going through a very small hole in a tube. Okay, if you want to have a look at that closely, there we go. Right, small hole in a tube, string goes through the small hole in the tube, classic presentation. Okay, used to demonstrate conservation of angular momentum, and the theory is this. Because you swing it around on a string, you pull it in, it goes faster, and there we have conservation of angular momentum. But the reality is actually quite different. Let's do some mathematics. Okay. The mass of the object. I've said it's 20 grams, it's actually 21.6 or whatever, but 20 grams is good enough. Okay, the radius. R1, 50 centimeters, half a meter. I have marked off half a meter on the string. It's over there, there's a blue mark on the string, and I've marked off 5 centimeters on the string, which is over there. Okay, I don't need to measure it, I'm sure you can see that's about half a meter and that's about 5 centimeters. The angular velocity, okay, this is where I messed up last time. The angular velocity, I'm going to try and keep it to about 1 revolution a second. From what I've seen, it's a little bit faster, but that's fine. Okay, so let's say that that's 2 pi radians per second. V1 is your radius times your angular velocity, which comes to 0.5 times 2 pi or pi meters per second. Straightforward stuff. Okay. Now we're going to do the maths of what the current scientific theory is using conservation of angular momentum, what it says when we pull in the radius to 5 centimeters, which is 0.05 meters. This little equation comes straight out of my physics book. It's an old physics book, but the new ones are still doing presenting the same theory. And the theory is that V2 must increase in order to conserve the angular momentum. The linear momentum must increase. The magnitude of the linear momentum must increase. They pulled that out of the, I don't know where, okay. But the theory is that V2 equals the radius 1 over radius 2 times V1, and since I'm reducing the radius by a tenth, I'm getting 10 times the velocity now. Okay, this is the theory, which is the equivalent of 31.416 meters per second, or close enough there too. If we apply this and work out the centripetal force, of which the equation is F equals mv squared over r, which is around about 0.02 being the mass, times the velocity squared over the radius and whatever, comes to 395 newtons, which is about the equivalent force that gravity exerts on 40 kilograms. Okay? And the angular velocity is omega equals V2 over R2 equals the 31.416 over 0.05, which is 6.2832 radians per second, which is the equivalent of 100 revolutions per second. Okay, near enough there too, right? Which is the equivalent of 6,000 RPM. Now, 6,000 RPM, most people never ever rev their car that high. A person who drives very lively will sometimes rev his car that high, and that's when he's really pushing it. Okay, that's to give you an idea of what kind of speeds of revolution science says we're going to be getting out of this little device. Okay, it's absolutely ludicrous, it's wrong. Okay. However, we're going to show you the presentation and you can decide for yourself. Okay. My theory, which is not accepted by scientists, I'm called ignorant by scientists. My papers they refuse to publish them, and you know, I don't know. But my theory is this. Okay, maybe this is the ignorant theory. Is this: the magnitude of the momentum is conserved. That's what I'm stating. And that makes sense because conservation of momentum is a reality. So, from that we have V2 equals V1 equals pi meters per second. So what I'm saying is that the original velocity of the object on the string is going to remain the same. Not the vector part of it, but the magnitude of it. Okay. Which will give us a centripetal force of F equals mv squared over r, blah, 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 fill it in, 3,95 newtons, or about the equivalent that gravity exerts on, equivalent force that gravity exerts on 40 grams. Okay. So, 20 gram mass, I'm going to feel 40 grams when I pull it in. I've got to pull more than 40 grams. All right. Angular velocity, well, angular velocity omega is V2 over R2 equals 3,1416, which we get from pi meters per second over the radius is 62.8 radians per second, which is about 10 revolutions per second, or 600 RPM. But 10 revolutions per second, well, you can kind of guesstimate that it is about there. Okay, that is the reality. Okay, this here is what the science is telling me, that I'm ignorant because I don't believe it. Okay, but in any event, you tell me. Okay, I'm gonna just run this little demonstration once more. It's at the first mark on the string, and I'm gonna pull it into the second mark on the string, and I'm gonna try and swing it at about 1 time a second. Let's do it again because I didn't get it all the way to the mark. But even so, I can assure you that that's not showing 6,000 RPM, and it's not taking 40 kilograms for me to pull it in. I pulled it in past the mark, so it should be even higher, the numbers. Okay. You tell me which is right.